content. So welcome to week 3 for our MET 136 live lectures. And so we have a series of topics that we're doing that we broke up into different sessions for this week only due to the amount of content that we have. And so in your course, you probably had some type of announcement about joining the live lectures, and there was a schedule, and we posted that information in the schedule in advance. And so if you have looked at that before joining today, you will have seen that for this week, we put a disclaimer that we were focusing on certain topics during each session. If time allows, we will go into the other content that was covered in a previous session or is yet to be held. So today, my focus is on sections 5.1 and 5.2, the session that was held on Wednesday evening, where we already have a recording down here for that. That main focus was on sections 3.3 to 3.5. And then I believe that lecturer was able to just talk about some overview things in 5.1, 5.2. So same thing with me today. I'm going to focus on 5.1 and 5.2, which I believe is part of your O3B content. And then if time allows, I can certainly go into other things. And then Saturday's session from 2 to 3 p.m. Eastern is going to focus on the last two sections, 5.3 and 5.4. We felt this was better so that we could adequately spend time with everything rather than running short on every little topic we wanted to talk about for you guys, since there's 7 sections this week. So that's kind of the layout here. So I'm going to get to our topics of polynomial functions and graphing polynomial functions. Like I said, you are welcome to put questions in the chat as I go through what I'm presenting to clarify anything I'm saying, or you're confused about what I said. You're also welcome to raise your hand in your reactions. So I want to go over some of the basic content. Now, I'm going to have a lot on this screen. All of this should be in a couple places in your course. One is in your e-text, and I'm gonna make that a little smaller so it all fits there. One is in your e-text that you can get from the Ivy Plus bookshelf within your course. And then the other is in the content within your modules within the course. Like there are some PowerPoints in there, and then you've also got supplemental videos and things. But I want to talk about some of the key terms and things that I'm going to be using before I get to the problems, because you need that to understand the problems. So these are things I would recommend you personally, keep a notebook for yourself with like key terms and things you want to talk that you want to learn, definitions, concepts. So you have that to refer back to as you're preparing and studying for your midterm, which should be next week. So it's right around the corner with things with that. So with that said, this whole section is about polynomials. And so we need to make sure we know what that is. And so it looks kind of scary, but when you look at it all together, but if you break it down, I want to highlight the different parts. So you're going to have coefficients, and that's going to be all these A's that have subscripts. And they start with a subscript of n, and then they decrease from there. And then you're also going to have the powers of x. And you can see that you've got an integer n that is used as the power, and then they go in descending order from there. So n, n minus 1, and then they keep decreasing. And technically, there's an invisible 1 on that x that's at the second last term. And then technically, there's also an x with a 0 on the last term that's constant, but recall that x to the 0 is equivalent to 1. And so we don't really write that there. And then the big thing is the largest value n at the beginning, when this is in descending order, is your degree. And so we want to make sure we are aware of what that is when I'm talking through examples here shortly and refer to a degree. And then also we want to make sure that we are focusing on our leading, I didn't want to say leading coefficient, leading well, yeah, I'll say leading coefficient. Our leading coefficient is going to be this first one. And together, if I take the a sub n and the x to the n power, that is my entire leading term. I don't have that typed on the screen here, so we'll write that on here, okay? So I just wanna make sure everybody's aware of that. If you take and look at that first term, you can basically say that that is similar to a power function. And so we're gonna use that information here shortly that allows us to figure out, well, what's going on? And it depends on whether or not we have that power n being a positive even integer. So that could be something like 2, 4, 6, 8, etc. Or if we have something that is a positive odd integer. So something like 1, 3, 5, 7, etc. Okay. And that tells us the behavior of what's happening. Now, this might look a little complicated and you don't know what these arrows mean, but basically that arrow means goes to or approaches. So that arrow there means goes to when you read this, or approaches. Okay, so I think, you know, a challenge for some students in math is just reading it. It's like a different language, literally sometimes. And so as x goes to or approaches infinity, the function itself, which is that power function, also goes to infinity. And so if it's a positive even integer, these all kind of basically resemble f of x equals x squared. So I might have something like this. And this is negative 1 and 1. And this is at 1. Let me scoot this over to actually match up with that. And if I keep increasing that power, what's going to happen is this is going to become steeper through the sides, and then it's going to become flatter and more kind of squished down and boxy, I call it, in between there as that number increases, but it still maintains that rough shape. Similarly with the odd ones, I can look at that and I can say, okay, I can compare this to resembling f of x equals x cubed. And so if you think about the basic graph of x cubed, in a quick little sketch, goes through 0, 0, 1, 1, negative 1, negative 1, and then it does this twisting shape in the center, kind of like that. Very rough sketch there. And so what would happen is as x goes to infinity, so as x goes off to the right, the whole function itself goes to infinity. So you see up here, it's pointing up to infinity. And these are some of the key points it goes through. Well, if I keep increasing the 3, 5, 7 for the odd power there, what's going to happen again is this is going to kind of be steeper through here, but still grow through these key points. And it's going to be flatter, therefore kind of getting closer to the x-axis here in the center, pass through that key point, and then become steeper again. So that's kind of how these are all related, okay? One of the things I'm going to get to in an example in just a second is real zero. So it's important to know that these 4 bullet items here are essentially all equivalent, okay? So if you know one, you know the other 3, okay? And so by that, what I mean is we call something a real zero, but when we say a real zero, it could also be the same thing as an x-intercept if we're referring to the graph. The real zero itself refers to the function, like the equation of the function. So different terminology, but really the same value. And then we can also refer to, I'm going to put this in parentheses because I think that helps some students visually. X minus R is a factor of your function. So you can take a function and you can have it in factored form. So you might have a series of these parentheses, and you might have multiple factors. So let's say I have x minus real 0, 1, and then x minus real 0, 2, and x minus real 0, 3, and so on and so forth. Because you can have more than one real 0, which means you have more than one x-intercept on a graph. And then all of those mean that you also have a real solution to setting your function equal to 0. So now if I take this f of x and I replace it with 0 equaling this x minus r1, x minus r2, x minus r3, etc., I can individually break up each of these into setting the linear factors equal to 0 and getting a solution. And that's why these also are the same values as our real solutions, okay? So again, these are all the same value basically, and same info for our function s. You know one, you know the other, and it's all implied, okay? What you can also have is multiplicities. So on all these factors I just wrote here up at the top, the x minus r1, x minus r2, x minus r3, etc., those are all our factors. If we have a power on our factor, that's our multiplicity. And it can be either even or odd, okay? And what it does is it tells us something about how that x-intercept, because that's that's the second bullet item I just talked about, how that x-intercept interacts with the x-axis. Does it touch it and pass through, or does it just, does it touch it and not pass through, excuse me, or does it cross through? And so what that means is, let's say hypothetically, got some axes here, and I have real 0, 1, which leads to an x-intercept on the graph, and I have real 0, 2, which again leads to an x-intercept on the graph. So I've got a point here and here that are my x-intercepts at R1 and R2. If I had a factor, say for R1, that had an even multiplicity, so I'm going to come up here and I'm going to put a 2 for the multiplicity as the power on that factor, what that would tell me is that my graph should touch the x-axis at R. So one possibility that could happen is my graph could do something like this, come down, decrease, touch that point, and then turn. So that would be touching, okay? That's one way it could do that. Alternatively, I could also say it started from the bottom, increasing, touched it, and then turned and came down this way. That's also touching it, but in each case, it's not crossing it. Okay, so I'm going to leave it like that. So let's say it touches like that. If I have a factor that has an odd multiplicity, so I'm going to take my first odd number I can think of that isn't 1, and let's say I have this be a 3 as a power on this factor for my real 0, R2. What that tells me is that it's going to cross the x-axis and go right through that point. So that means over here at R2, because of the way I left my picture at R1, somehow this is going to have to turn and come back over here so that I can cross through my intercept at R2 because of the odd multiplicity. And then maybe it ends this way, going off to infinity. So we've got a touching the x-axis at R1 because of the even multiplicity, which is the power on the factor, or we have a crossing at the real 0 or x-intercept because the factor had an odd multiplicity, okay? And so you piece these things together like a little puzzle of like, how is the shape of your graph going to look? So I mentioned here that I had to have this turn somewhere. So here is a turning point. It changed directions. Where this is touching is also another turning point because it's where I change directions. And so we can have a certain quantity of those. So remember at the beginning, I went over the different parts here. And I said, one of the things that's important is this degree. That's going to be related to how many times this can turn. So down here for turning points, you look at the degree of the function. So it's degree n, and then you end up with at max or at most one less than that. So this is n minus 1. So let's hypothetically say if n equals 4, then this is at most 4 minus 1 or 3. I'm just going to abbreviate here, turning points. Okay, and that's the relationship. So it's important to know that degree number because once you start drawing your picture, you want to make sure it's turning in the right places and not too many places, okay, for that. And then the last thing before I jump into putting all this together in a problem for you is we look at what's called end behavior. So the end behavior is where do the arrows point at the far ends of your graph? And it all depends on that leading term. So again, remember at the beginning, I focused on saying we've got this leading term that's made up of the leading coefficient and then the power of x that has my degree on it. And so that is a power function when we look at it as a whole. And so based on that, and whether or not we have an even power or we have an odd power, the ends of our graph do different things. But it's also combined with the leading coefficient being positive or negative. So then the other part of this is my leading coefficient can be positive and my power is even, or the leading coefficient can be positive and my power is odd. Or I can have a leading coefficient that's negative with an even power for my degree, or I can have a negative leading coefficient with an odd degree. And so what you should be focusing on is where do the ends of these graphs point? Okay, that's what we mean by end behavior. So we can kind of ignore the middle where it's doing all these little ups and downs, increasing, decreasing, and turning points when we focus on end behavior. So notice when you have an even degree, okay, they point in the same direction, either both up or both down. And whether it's up or down is dependent upon the leading coefficient. If the leading coefficient is positive, they're both going to point up. If the leading coefficient is negative in the second picture, they're both going to point down. Okay. Then if you change the degree to being odd, then you get the second set of two graphs. And notice the ends, they are split. It's like our hair. Split ends, okay? They go in different directions. And so you can see that in the first one, when your leading coefficient is positive, it is down first and then up. And then when it's a negative leading coefficient, it flips to the opposite and it's up on the left and down on the right, okay? And so one thing that might help you with that is if you can think of x squared with either +1 or -1 x squared, you get the first two pictures if you just think about the ends of the graph. If you look at the second two pictures with the split ends, you can think +1 x cubed or -1 x cubed, because if you think about the ends of those graphs, again, not accounting for things in the middle, they have those same type of split ends, okay? So that's kind of my overview. Now I'm going to get into the problems. So again, as I get into the problems, if you've got questions, feel free to ask. I don't see any questions in the chat at the moment or any hands up about any kind of the groundwork that I've laid here. So I'll get right into a problem. So I'm pulling from sample problems that are related to your homework assignment that kind of talk about the things that I just went over. So I pulled this from part B of your Module 3 homework, and this is similar to question 11. Again, the problems kind of alter and change in terms of like the numbers and quantities and things, but structurally, they're the same type of concepts. So you should see other problems like this and not just problem 11. But let's look at the information that they've given us, okay? So they want us to form a polynomial. So what does that mean? That means find the function f of x in equation format, okay? And so you can see down here in the answer blank, it says type a polynomial with integer coefficients and a leading coefficient of 1 in the box below. And they already have the f of x part written, so f of x equals, and then it says to simplify our answer. So we're going to have something that is f of x equals blank, and we're just putting the stuff there after that. So we have to come up with the equation. So what do we know? Well, it has specific zeros. So the zeros, there's two of them. One of the zeros is a value of -4. The other one, after the semicolon, is a -3. Those are the zeros, okay? So you have to look carefully where the commas are and where the semicolons are so you understand what they're giving you. So the zeros, which are the same thing as, let me go back to the slide I had with the 4 bullet points. Here we are. The zeros are the same thing as your x-intercepts. They are the same thing as your real solutions. And they are also what you can use to form your factors. And I'm going to focus on factors, okay? So if they tell me that these zeros are -4 and -3, then we know if, I'm going to call it R1, is -4, then we have the factor x minus -4, because we would have x minus R1. And if, say, the real zero, R2, is -3, then we have the factor x minus -3 for R2, okay? Now, we wouldn't normally leave it like that. We would take that subtraction of a negative and we would write it as plus. So what we know so far is f of x is something with a factor x plus 4 because of the minus of the negative, times an x plus 3, again, because of the minus of the -3. And those factors get multiplied together, okay? That's what we know so far. The next thing we know is about the multiplicity. The multiplicity that goes with the 0 of -4 is a 1. So remember, the multiplicity was the power that goes on the factor. So that means down here, x plus 4 has a power of 1. Now, I don't have to write that 1, and you typically won't see that 1. But for explanation purposes today, I'm going to write the 1 so you're aware of that. And then the other multiplicity is 2 that is in reference to the 0 that is -3. So on the factor that goes with that 0, which is x plus 3, it has to have a power of 2. There are my multiplicities, okay? And then overall, we are told that the degree is 3. So to make sure that the degree is 3 means if this were multiplied out in the format that looks like this way that we write a polynomial, individual terms, and not in the parentheses, then the highest power at the beginning for the degree I would see would be a 3. So I come back over to my problem and I look at that and I say, okay, well, this tells me to simplify my answer It also tells me to use a leading coefficient of 1. So in front of all this, I'm going to put an A because that's my leading coefficient, abbreviating there. That could be any number. It could be 3, it could be 7, it could be -20, it could be 1/2. Well, actually, it couldn't be 1/2 because it says integer coefficients. So scratch the 1/2. But it could be positive or negative because it says integer coefficients. But they're specifically telling me to use a 1. If they had specifically told me to use a 3, I would have put a 3 where the A is. If they told me to use -5, I would put a -5 where the A is. But they're telling me to use a 1. So I'm going to have f of x equals 1 times x plus 4 to the first power, and then times x plus 3 to the second power. And it says to simplify your answer. So what this means is I need to expand / multiply this out, okay? And once I have it multiplied out, I'll be able to verify if my degree matches and is 3 or not, okay? So I suggest starting over here with the x plus 3 squared, because that means if you need to, if you can't do that in your head, when you're going to be prone to making mistakes, write that out. It means x plus 3 times itself twice, which means then if you multiply that out, and you can use FOIL or other methods, that gives you x squared, and then your outer and inner terms become plus 6x and then plus 9. So now that's multiplied out, and you still have this x plus 4 raised to the first power, and this 1 that I'm not going to write anymore as a coefficient because I don't need to because it's a 1. But if it was a 3 or a 5 or a -7, I would still continue having it there. And then I need to use the distributive property to multiply that out even further. So you're not done and have it simplified until you've done all this. So that means I'm going to focus on the x, multiplying to each of these 3 terms in the trinomial. So I'm going to get f of x is x cubed plus 6x squared plus 9x. Then I'm also going to focus on the 4 getting multiplied to all 3 of those in the trinomial, adding on to those terms, and I get plus 4x squared plus 24x plus 36. So now I've distributed it, but again, because it says simplify, I need to collect like terms. So I take a look at this and I say, okay, it looks like I've got some x squared terms that are the same, and it looks like I have some x terms that are the same. And so I collect those like terms. And so I get f of x is x cubed plus, taking the pink underlined terms of x squared, I get a total of 10x squared. Taking the green underlined terms of x's, I get 9 plus 24, and that's plus 33x, and then my constant term 36. So this is what I would type in that box, okay? And notice they already have f of x equals, so I don't need to type f of x equals. Now, if I'm writing this on paper, like what I'm writing on the screen, and you should be writing your work on paper at your midterm next week, and then that's getting collected either from a proctor on campus and will be scanned and emailed to your teacher, or you might be taking a virtual appointment and then you are scanning it and uploading it in your course to your teacher, and they're going to grade that for partial credit. So make sure you've got your stuff written out with details and steps in your work. So that's how I would do that. Okay, so that's my first example. I don't see any questions. But again, as a reminder, you can raise your hand virtually and I can call on you, or you can put questions in the chat if you need to. I'm going to go on to the next problem since I don't see any questions. And this one, I have it set up where you're going to see the answers already here, because it was going to be easier for me to do this and then just explain like, hey, how do we get these answers, rather than me trying to flip back and forth to MyLab on the screen to say like, you know, how can we look at this part by part? I'm sure you guys know when looking at your homework, when you have a multi-part problem, you only see one part until you put the answer in, and then you have to wait to get to the next part. So I wanted to show all parts together. So I've got it like completed already, but I'm going to explain how do we get all this, okay? So again, this is pulled from your homework. So you'll see similar questions like this in your homework, like number 14. You might have other problem numbers that are also like this that aren't problem number 14. But let's break this down. So it's got parts A, B, C, and D. So I'm going to focus on part A first here, which is taking this function that, notice this is already in factored form, right? So factored form is nice because remember my bullet points I showed back here. If you know something about the third bullet, x minus r is a factor, well, then that tells you something about the value of r being a real zero or an x-intercept and things like that, okay? And a real solution. So factored form is useful. So if it's not already in factored form, then you should probably factor it so that you have it in factored form. And that'll be, you know, useful for you with that. And so the first question is about the real zeros. So because it's in factored form, the real zeros should just be the values that are after the minus sign in each of those factors, right? And so I see that I have a factor of x minus 3. I also see that I have a factor that is x plus 7. So I'm going to focus on those two. So my factors of x minus 3 and x plus 7. And our factors are normally x minus, you know, the r value for the real zero. And so this x plus 7 is really the same thing as x minus a negative 7, okay? Because the formula itself for that factor has a subtraction sign in it. And so that tells me the actual real zeros is what follows the subtraction sign. So when I rewrite x plus 7 as x minus a negative 7, the real zero is actually the negative 7. So a common mistake I see students make is that they say that the real zero is positive 7 because they're looking at the factor, not what follows the subtraction sign in the factor. And so over here, I would select option A out of this question because I did find real zeros. And then it says to type an exact answer, use integers or fractions, and separate them with a comma. So that's what we did. I have a 3, comma, negative 7. So those are my real zeros for that, okay? Then, as part of that question, it says to also find the multiplicity. So again, the multiplicity comes back to the powers on the factors. So there's an invisible 1 here on x minus 3. And so for the multiplicity, I've got the factor x minus 3 to the first, and I've got x plus 7 to the second. So the multiplicity is the 1 and the 2. And this is where you want to be extra careful also. This is another place I see students make mistakes. The way you enter it, because they don't want to give away the answer to part A, telling you that, oh, your real zeros are 3 and negative 7, they are referring to the real zeros as the larger zero and the smaller zero. So they're kind of directing you to the fact that you have 2 of them and one is bigger than the other. So notice the 3 versus the negative 7. The negative 7 is the smaller real zero, and 3 is the larger real zero. Because on a number line, this is 0, 3, this is not to scale, so bear that in mind. Negative 7 is smaller and 3 is larger. So don't get confused as to which box you're putting the number in. So therefore, the larger real zero is the 3. So that multiplicity is the 1, because the 3 was the larger real zero, okay? And then likewise, the -7 was the smaller real zero, because this is, again, x minus -7. And its multiplicity is 2. So that's the order that I put them in the box, okay, for that. And so again, if you made a mistake with the multiplicities, or sorry, with the x plus 7, you might have gotten smaller and larger factors mixed up with each other, okay? So now we've got our multiplicities. So now I can go on to part B. Part B is then asking us, determine whether the graph crosses or touches the x-axis at each x-intercept. Again, x-intercept is the same thing as real zeros. Those are the same values. And so the multiplicity is what tells us if it crosses or touches. So remember, you look to see if your multiplicity is even or odd. So the multiplicity of the larger zero was 1. That was odd. And odd multiplicities tell you that then at the larger x-intercept or real zero of 3, okay, because that's odd, you're going to choose crosses. And I believe in my lab, it's like a drop-down menu. You don't type in the word, you just select it. And then likewise, looking at the smaller x-intercept, or that's the real zero of -7 on this problem, then that was even. And because that was even, you're going to select from the little toggle menu touches, okay? So then, so you can see how, each piece builds on something else and it kind of trickles down to other parts of the problem. So then part C asks us for the maximum number of turning points, and that is related to the degree of our function. So I'm going to rewrite our function down here so I don't have to keep scrolling, okay? So our function was -3 times x minus 3, and then x plus 7 squared, okay? So our degree would be if this were multiplied out in descending order, that leading term, what's that power on that? So imagine if this was multiplied out, this x plus 7 as a group squared would eventually lead to something that starts with x squared and then other terms. And then this linear factor here, because this had a power of 1 on the factor, that would just be an x and then, my x minus 3. And then I've got this -3 coefficient that doesn't have any powers with it. So if I put these two together, that's going to give me an x to the 3rd power, which means 3 is my degree, okay, which is n. And so therefore, for the turning points, remember that is going to be n minus 1. So in this case, this is 3 minus 1, which is 2. And it's always a whole number. It's not an integer. Your maximum number of turning points can't be negative, okay? So that's why that's a 2. Again, a big mistake a lot of students have is they get confused and they think it's the same as the degree, and it's not. It's 1 less than the degree. That's why I took some time at the beginning to kind of go over some of the basic rules with that. And then you can do part D, which is type the power function that the graph of f resembles for large values of x. Basically, this is talking about end behavior, okay? And so that is related to the leading term. So now over here, I already said I'm going to have this x cubed, but now if I also had this -3 coefficient in front of this, then this is my leading term. If I had multiplied the whole thing out, and I don't need to actually multiply the whole thing out, I just need to look at like, what would the front of it be, okay? And so, because that's my leading term, notice that's exactly what I put in here. And the computer already had y equals. So the power function is an equation but the computer already put the y equals, so I don't have to type the y equals. But if I was writing this on paper and showing that to my instructor for my work, I would write negative y equals negative 3x cubed on paper. In my lab, you're just typing in the actual part after the y equals, okay, with that. All right. Okay. So again, I don't see any questions so far, but you are welcome to ask questions, but that is the end of that problem. So then that leads us to, how do all these things work together to create a graph of a polynomial function? And so that's in the second section of chapter 5. And here are kind of the basic steps. So this is 5.2, graphing polynomial functions. So basically it's taking everything I just talked about in 5.1 and applying it so that then at the end of everything, you also draw a graph, okay? And so we talked about things with end behavior. We talked about finding x-intercepts, but we can also find y-intercepts, and that should be a skill that you already had prior to this section. We can talk about finding real zeros. Again, the real zeros are going to be the same thing as the x-intercepts. And then we also talked about their multiplicity, because that multiplicity is then what's going to tell us about the graph crossing or touching the x-axis. So again, one thing leads to the next. Then we talked about how you can have maximum number of turning points. Again, that's n-1, where your degree is n. And then you're going to pull all that together, and you are going to draw a complete graph. You're going to pick a y-axis scale to fit everything on there, and then any additional points you need in between your x-intercepts, okay? So I'm going to walk through a problem that has a lot of parts to it. So if you've already started the homework for this week, you probably noticed that this has all the way up to part E. And again, for the ease of not having to flip back and forth to my lab versus the screen I'm writing on and be able to see all the parts, I have the answers already here for the problem. I want to explain, how do we get that? Okay. If you were starting this from scratch, how do you know that those are the answers that you enter? And so it says to analyze this polynomial function, and it gives it to us again in that factored form. So again, factored form is nice. If it's not already in factored form for you, which I think most of them are, then put something in factored form yourself, and that'll be a good start to the problem. A lot of times students say, I don't even know where to begin, right? I'm sure many of you have said that to yourself or to a teacher or a tutor. And so a tip is, again, look for, okay, do I have the problem in the right format? And then is there something I can do to change that into a better format to make it easier to work with? So we've got it factored. So let's just get started on the parts. So part A is determining the end behavior. And so it wants to know what function does it behave like where the arrows point at the end of the graph. And that is where you want to take and imagine, look for the power function as the leading term. So you want to expand this basically. So if I've got x plus 2 and x minus 4 cubed, this portion here with the x minus 4 cubed eventually would mean I'd have an x cubed and then other terms, because this means x minus 4 times itself 3 times. And so because of the x and the cubed, I know I'm going to have something that starts with an x cubed there. And then I've got this x plus 2 term. So then I know when I go to distribute, I'm going to put together my x and my x cubed. And again, this is like an x to the first, so I'll just overemphasize that that's a 1 there. So that when I bring them together, I'm going to get something that is going to be with an x to the 4th. And then I look at the coefficients. So there was a -4 in front of all this, that if I multiply these two front terms, that -4 can continue to be multiplied with it. So that's the whole entire leading term, because there's the other things following it, but we just care about that leading one, because in descending order, that should be the highest power. So that is what I put over here in my answer box. And again, notice that they already wrote the y equals. So on paper, or like here on my screen, I would write it with y equals, but the computer already has it there for you as a template, so you don't need to enter that part, okay? Now, what does that tell us? Remember, the last part, E, is we're gonna have to draw a graph. Now, I realize this is multiple choice, but you should never approach a multiple choice problem of, let me just see which one I think fits. You should basically create a graph yourself, and then if you've done it right, it should match one of the ones that's there, okay? So what this tells me is that because it's an even power, I have to have the same ends, either pointing both up or both down. But because the leading coefficient is negative, then that tells me, so that value is less than 0, it's negative, they're actually going to both point down. So if I was looking at just, a set of axes, the ends of my graph, wherever they are on each side, are going to point down. That's what that tells me so far, okay? So keeping that in mind as we're going to draw a graph. Then I get to part B, where I'm going to talk about the x-intercepts and the y-intercept of the function. So if we focus on the x-intercept first, x-intercept, remember, means same thing as real zeros. So because it's in factored form, I can find those easily. So my factors are x plus 2, which would have been x minus a negative 2. So therefore, my real 0 or x-intercept value is a negative 2. And then I had the other factor that was x plus 4, no, x minus 4. Let me write it correctly. It was x minus 4. So therefore, the other real 0 or x-intercept that I have is just 4. And so that's why I have comma 4. So again, if you look at the directions, it says to type an integer or fraction, use a comma to separate answers, type each answer only once. So if it were to repeat and I had another factor that ended up with a real 0 of 4, I wouldn't list it twice. The other thing I'm doing is I'm not, my pen back, not the highlighter, I'm not writing ordered pairs because the directions don't say to do that, okay? So if you were to enter -2, 0, comma, 4, 0, that would be wrong. And I see a lot of students make that error because they don't read, or sometimes they do read, but they don't understand the instructions when it says type an integer or fraction, use a comma to separate this, and maybe in a different section that you've already had prior to section 5.2, maybe you did write the x-intercepts as ordered pairs because maybe that's what those instructions said. And so that's possible. So, one of the things, again, kind of think of math as a language, you got to follow what it's saying, and there's different formats to write things. So just be aware of that, because you might know completely what you're doing, but simply because you put it in the wrong form, the answer is still going to be wrong, okay? So we want to pay attention to the form as much as we pay attention to the actual value. Okay, and then I can find y-intercept. So y-intercept, we have to think, okay, well, how do I find that? Well, this goes back to like pre-algebra. When you have a y-intercept, the x value is always 0. So y-intercept, I'm going to do that over here where I have some more room, is find f of 0 for the y-intercept. So my function, if I plug in a 0, I'm going to have -4 times 0 plus 2 times 0 minus. So I compute that. This is -4 times 2. If I cube -4, be careful, it's -64. So then when I multiply that all together, I'm going to end up with a positive value, and that's going to give me the positive 512. And so it's the 512 that comes here. And notice again, it says type an integer or fraction. So not 0, 512, not an ordered pair, okay? On a different problem that might ask you to do that as an ordered pair, but not on this one, okay? So then it says to determine the zeros. Well, remember, I just set it up here that the real zeros are the same thing as the intercepts. So this question, notice, has the same answer. Okay, so again, if you know that terminology, and that's why I started this whole session with kind of going over some of the basics. If you understand that terminology, that x-intercepts and real zeros are the same thing, it's just that x-intercepts are basically referring to what you see on the graph. These are the same values. So once you have that answer, you just use that answer again. So now it has to do with the multiplicity. So again, the wording sometimes throws students off here because the program doesn't want to lead you as to what value you're going to get for these zeros. So they're going to refer to these as the lesser zero and the greater zero. So notice that -2 is the lesser or smaller zero, and the 4 is the greater zero. So greater zero, lesser zero. So you want to make sure you're looking at the right factor with the appropriate zero so you don't get all the answer blanks mixed up. And so because the -2 came from this factor, x plus 2, that had a power of 1, its multiplicity is 1. And because that is odd, then you would select that it crosses the axis here, okay? So then you go to the greater zero, which was the 4, and the greater zero, which was the 4, came from the factor x minus 4, and it has a multiplicity of 3 as a power. So you enter the 3 for the multiplicity, and because that is also odd, you're going to select that this crosses. Now, what it also did is it asks you to put the value of that lesser zero over here as x equals that number. So notice you're entering that x-intercept and the real zero, and then also when you refer to the lesser zero, you're entering that same -2 in multiple places. You want to make sure you really get that correct because you're entering it in different places that could be wrong. And then likewise, for the greater zero, they're asking you to enter in that greater zero over here to refer to that, okay? Then part D is maximum turning point. So we look at the degree n for all of this is basically adding those powers or looking at this power from your first equation with n behavior, and that's a 4. So the degree is 4, so then n minus 1 is 3, and so that's how we get 3 max turning points. You can have fewer than that, but not more than that. And then we come to the graph. So rather than just kind of doing eeny, meeny, miny, mo, which one do I think is correct? I mean, you can do some process of elimination, right? Because at the top, I said, what does it mean for this n behavior function? Well, the two n's have to point down and be the same. So I know immediately, because it's multiple choice, I can rule out these two because the n's are pointing up. But if you are just graphing this from scratch, you know, you wouldn't be able to do that. So then we come to these other ones and we think, okay, well, what is it going to be? So if I were to piece all this information together and give myself some graph paper, what I basically know is somewhere the ends of my graph are going to point down on the left and the right. I know that my real zeros were -2 and 4. So if I'm going by ones, here's -2, here's +2, here's 4. So I'd have a point here and a point here. I also know that I have to cross. So because my end behavior has to go down, I'm going to actually move this over a little bit. I know that this is going to have to continue coming up here, and I'm going to have to cross here. I'm also going to have to come up here, and I'm going to have to cross here because of the multiplicity. So now I got to figure out what else is going on. Well, remember we had a y-intercept of 512. So like if this is 100, 200, 300. So see, I changed my scale, 400, 500, 600. Then I know I have a y-intercept like roughly here. Somehow it's got to connect, but what else is it going to do? So you can take and make like a little chart for yourself or a number line where you can pick values to the left of your first x-intercept. So like -4. I already know 0. Maybe I can put in +2 because that's in between my y-intercept and my next x-intercept of 4. And that, or maybe I can put in 3, and then you calculate what are those values, and then you can plot some points to see what this is going to look like. Because this is going to have to come up here. I have to have 3 max turning points. So I got to figure out, does this just connect like that? Probably not. Or does it connect in such a way that maybe, you know, it turns into something else? Like, what does it do? And so that's where this missing part of like, how do you connect that? You can just plug in some other values to plot some points to figure that part out. So back over here, if I zoom in on this, you can see these are a little bit different. So if I've already got my 512 amount here and here, and I've got my real zeros at -2 and 4, looking at the scale, I can see like here's a -2, but actually no, that's -4. So I see that's in the wrong spot, that's in the wrong spot. Well, then I know this one is the correct one. But if I'm drawing it myself, again, I could plug in other values in between here to see what this is, okay? So you can get a pretty good picture and then just fill in the details with adding in some other points with your function to see what it's going to do completely. So that is exactly what I wanted to finish today. So the last thing I want to just put back up on the screen for everybody and then also put in the chat is our survey. So I'm going to go ahead and put this in the chat. If you could fill that out for 2 reasons. Again, it will log your attendance here, and it will also share what you want to say. Let me paste it there. It's in the chat. So you can click on that directly. And give your feedback on things that, you know, maybe we can take into account for the next session to change. No guarantees, but we can certainly take your feedback and see if it is something we can accommodate and change. I know some people have already given some feedback. They wish they had longer sessions. I don't know that that's something we can accommodate right now, but we can certainly consider that for the future if we continue on with this in another part of the term. So thank you for attending today. Please do fill out that survey. Feel free to attend the session that is on Saturday as well, if that works with your schedule. And you can always come back to that schedule document that will have the recordings in it, usually like by the next day. If you also want to go back to see anything. Tomorrow, the focus is on section 5.3 and 5.4 from that lecturer. And then Wednesdays, again, already went over the stuff from chapter 3. So thanks for attending, everyone. Have a great day.